Good afternoon. Once again, it's my pleasure to introduce Dr. Fran Bagenal. Dr. Bagenal received her PhD from MIT. She's interested in planetary magnetospheres. She's also interested in the solar corona. Today, once again, she'll be talking about the space environment. So without further ado, here's Dr. Bagenal.
Thank you. I want to start with some limbering up exercises. I want to recap on what we went over on Monday, and so that to make quite sure that you're really familiar with the sort of environment that we're talking about. Okay, so we're talking about the low Earth orbit. Now, where is the low Earth orbit? Low Earth orbit is where most of the satellites are. What sort of altitudes are we talking about? Come on.
250 kilometers.
250 to 500 kilometers, okay? Now, what is the main constituent of the neutral atmosphere at low Earth orbit, about the 500 kilometer level?
Nitrogen?
No, that's the dominant constituent at what that we breathe, the air that we breathe at the ground. But by the time you get up to higher altitudes, the lighter gases dominate, such as atomic oxygen, as you mentioned. Okay. So that's a single atom of oxygen. And you remember I showed you a picture of the shuttle glow, the glow around the shuttle, and that's evidence that the shuttle is moving through a neutral material, and it's the glow, oxygen, neutral oxygen glowing, interaction with neutral oxygen that makes the gas glow around the shuttles. Okay, now what sort of pressures are we talking about up there?
10 microns.
Not microns, bars. Okay, remember, unit of atmosphere is a bar, is the atmospheric pressure here on the ground, and when you go up, it obviously decreases very rapidly, exponentially, and by the time you get out to low Earth orbit, we're down by 9 to 10 orders of magnitude. Okay, that's a factor of a billion or more, down to 10 to the minus 9, 10 to the minus 10 bars. Okay, now one of the concepts we introduced is that of the mean free path. What is the mean free path? What does that mean? Mean free path of a molecule or an atom? It's the average mean equals average mean distance between collisions. Okay. Can anybody remember what sort of values are we talking about at low Earth orbit? What is the mean sort of distance between collisions? A kilometer, right? Kilometer, or as much as 10 kilometers, okay? So it could be, it's a lot larger than the scale of a spacecraft and so on. And so the atmosphere is tenuous, there are few collisions, and a lot of the particles are sort of moving around, not so much as a gas, but a collection of particles, okay? Less of a fluid, more like a bunch of particles. Okay, now what about the temperature of the atmosphere at these sort of altitudes? Do you want to give me a ballpark figure for the temperature of the atmosphere?
11,000 K.
11,000 K. That's a little high. Okay, I know what you're thinking. You're thinking of 1 electron volt. Remember we had that comparison. That's the sort of energy of the charged particles. But the neutral particles, those atomic oxygen particles that we saw around the shuttle, they're not quite so hot. It's sort of went off the scale of that diagram, and the right-hand side of the scale was about 100 degrees Celsius, okay? And it goes up somewhere. We're in the thermosphere. Remember that region of hot gas, the upper part of the atmosphere. And the temperatures are, say, on the order of, depending actually a lot on the solar cycle, between 100 and, say, 300, 500 degrees Celsius. And actually, when you get up to numbers like that, it doesn't really matter whether you're talking Celsius or centigrade. Remember, that difference of 270 is not such a big deal. Okay, so this is a very hot gas out in the upper part of the atmosphere. Why is it then that the astronauts that go on a EVA, how come they don't get burnt? You know, they're walking around in this hot environment. I mean, the low density, that's the key issue. Why is it what is it about the low density that means that they don't get burnt?
Particles are what carries energy, and they're not colliding with astronauts often.
Right. The particles are the things that are carrying the energy, and if there's very few particles, then there are very few of them hitting you, and so there are very few of them actually transferring that energy onto you, the person putting the hand out. Yes?
Yeah, you were talking about that the other day.
Yeah?
And the thing that came to my mind was heat capacity.
Yeah.
The element has very high heat capacity, much more than your hand. So it burns you, but if your molecules have much lower heat capacity than your hand, so it's not going to burn you.
Right.
It's a matter of, that's what I was...
Yes, and heat capacity will depend on the density of the material. Right.
Yeah.
So it's the same way, different way of looking at the same thing. Yeah.
Oh, okay.
That's a good.
That's right,
good-
you said density, that's right.
Yeah, it's connected through the idea of density. Okay.
Right.
Okay, so, or pressure, if you like, because really it's the flux of particles that are hitting you. Okay, good. So, we're talking about a low density environment. It's hot. Okay, why is it hot? Not a trick question. Very easy.
Radiation.
Radiation. Remember, that's a tricky word. What kind of radiation are you talking about?
The opposite of particle.
The what?
Opposite of particle.
Opposite of particles. Right? You got it. You got it. What are the particles? What is it? What is the opposite of particles? What are we talking about?
Electromagnetic.
Electromagnetic radiation. Great. You got the idea. The right word is electromagnetic radiation, and that is not physical particles that have mass, but massless particles called photons. Okay, we talk a lot about photons. And photons are electromagnetic. You can think of them as particles of electromagnetic energy, but they're massless particles. They don't carry mass, but they carry energy. They carry the energy associated with electromagnetic radiation. Okay, and this electromagnetic radiation comes from where?
Sun.
The sun. Okay, so solar radiation is pouring down onto the upper atmosphere and heating it up. Okay, and if it's heating it up, then that means that it's being absorbed by the particles in the upper atmosphere. And what happens when these neutral constituents, the atomic oxygen and so on in the upper atmosphere, gets bombarded with photons, with radiation from the sun?
They ionize.
They ionize, okay, to produce this layer of ionization. What do we call a layer of ionization? The ionosphere. And we have sunlight coming in. It's a layer, remember, because we have sunlight coming in. And to deposit its energy, it's got to start hitting material. So there has to be sufficient neutral density there for it to hit and ionize. But at the same time, you don't want to have too many collisions so that the ion and the electron that are produced in this ionization immediately stick back together. Okay? So if you go lower than the ionosphere, the ions and the electrons stick back together and you're left with a neutral particle. And so that's why we have a neutral region at the bottom and an ionized layer in the middle of the ionosphere. Okay, so above, in the uppermost part of the atmosphere, above the region of low Earth orbit and so on, there's a region where the mean free path is very small. Most of the neutral particles can escape. They go on large trajectories out of the atmosphere. Some of them remain bound by gravity, so they go into orbit, if you like, around the Earth. Sometimes they just go on a large parabolic orbit and come back and hit the atmosphere. But it's really a region where you can't really talk about the atmosphere as a fluid. You have to think of it in terms of particle dynamics. And below that, we have the environment of the weather environment down at the bottom, where you can talk about stuff in terms of fluid dynamics. Okay, so now let's think about what happens to those charged particles, the upper part of the ionosphere. Those particles that escape move out beyond the atmosphere, and because they're charged, they're controlled by electric and magnetic fields, okay, particularly the magnetic field of the Earth. What do we call the region that is dominated by the Earth's magnetic field? The magnetosphere, okay, the sphere of influence of the magnetic field. And in close around the Earth, it's pretty much dipolar, like a bar magnet, with the sort of ears, magnetic field lines going around. And the particles from the Earth's atmosphere that escape above the atmosphere are trapped in this magnetic field. And what do the trajectories, what are the paths of those charged particles look like? Somebody want to wave their arms at me and show me what the trajectories look like? Great, okay, it's Tom's, give us a demo. They do more than that. Go on all the way around. And then what? And then what? And then they go all the way back round again. Okay, great. They spiral around the field from hemisphere to hemisphere, bouncing at the strong regions of the magnetic field close to the Earth, like this, to and fro. Okay, great. But what happens, though, if the field is not strong enough for them to bounce? They come around and they hit a region of weak field, such as the South Atlantic anomaly that you read about in your reading. What happens to those particles? Doesn't bounce, goes into the atmosphere, bombards the upper atmosphere, and causes further ionization. Okay. What do we call a region of trapped radiation around the Earth? The Van Allen belts, or the radiation belts, named after Van Allen, who discovered them with the first explorer experiment back in 1957. And these are, what do they comprise? What are the particles we're talking about here?
Protons and electrons.
Mainly protons and electrons, with a few heavier ions, some oxygen ions from the Earth's atmosphere. What if these ions came from the sun? What do we have other than protons coming from the sun?
Hydrogen and helium.
Okay, well, ionized helium, and if you strip off both electrons of the helium atom, you'll get an alpha particle. Okay. And the negative ions, negative charged particles are electrons. Okay. Okay. Now, where are these radiation belts? Where are they in relation to geosynchronous orbit? First of all, where is geosynchronous orbit? What distance is geosynchronous orbit? 6 Earth radii. It's about 40,000 kilometers. And where is that in relation to the radiation belts? Inside or outside? Well outside the radiation belts, which is nice. It means that why would we want to put satellites in geosynchronous orbit? Apart from the fact that they'd be outside the radiation belts.
Stationary.
They're stationary. What do you mean by stationary? Stationary relative to what? They're in orbit. They're moving.
They're stationary relative to the point on Earth that they're at.
Relative to the point, a point above
Above
the surface of the Earth. Okay. So that means their orbital period is what? 24 hours. Okay. So these are outside the radiation belts, the geosynchronous orbit. What about are they inside or outside the magnetosphere?
Inside.
Largely inside. Now, that's a bit of a trick question because occasionally, very occasionally, the solar wind gets to be so strong that it pushes the magnetosphere in close inside geosynchronous orbit. That only happens maybe once or twice per solar cycle, and I'll come back to talking about that in a minute. But occasionally that happens, that the magnetosphere gets pushed inside geosynchronous orbit. Okay, so what do we have outside the magnetosphere? What happens if you go out? There's empty space. What are we sitting in if we go outside the magnetosphere?
Solar wind.
The solar wind, okay? Material coming from the sun. What does that material comprise? What are the components?
Particles.
Charged particles? Which charged particles?
Well, you said the alpha particles.
Some alpha particles, but it's mainly which two? Our favorite charged particles. Protons and electrons. That's what you get when you ionize the main constituent of the universe, hydrogen. Okay. Now, what sort of densities are we talking about? Particles per cubic centimeter.
5
Few.
to 10.
5 to 10. You're reading your notes. Yeah. Okay. 5 to 10. Few particles per cubic centimeter. But without looking at your notes, what kind of speed is this solar wind? The wind speed? 300 to 400 kilometers a second. And what is the Mach number of this flow?
10.
It's high. It's high mark flow of about 10. Okay, so we have the solar wind, we have the magnetosphere. The solar wind comes in towards the Earth. Does the solar wind hit the surface of the Earth? No.
Shock
What does
wave.
it hit? What does it hit?
Magnetosphere.
It's the magnetosphere, okay? And so you have the ram pressure of this solar wind coming along, and you have the magnetosphere. What is resisting the ram pressure of the solar wind?
Shock wave, shock front.
No, that's what you get in front of the obstacle is the shock wave, the shock front, because it's a supersonic flow. But what is the actual obstacle? Okay, the same way that you have the jet is the obstacle to the wind that it's flowing through, and you get a shock front in front of a supersonic jet. What is the equivalent of that jet to the supersonic flow in the solar wind? Some obstacle we've said is the magnetosphere. But what is it that's resisting that ram pressure? Okay, it's a magnetosphere. I mean, it's a few particles. I mean, it's the magnetic field. Okay, the magnetic field has a pressure. Okay, associated with the field, the magnetic field, and it's the pressure of the magnetic field that is resisting the ram pressure of the solar wind. Okay. And as we said, because it's a supersonic solar wind, we have the shock front in front, the bow shock. Okay. So, what I want to do now is, yes?
How would you measure that resistance?
How would you
measure that? What do you call that pressure?
Okay, you can measure the ram pressure of the solar wind. That's just the density of the magnetic field, a half rho v squared, half times the local mass density of the solar wind. And you know what the mass density is. It's just the number of particles per cubic centimeter multiplied by the mass of those particles, those protons. And V is the ram speed, the solar wind speed. Okay, so that's, you know what that is. You can go out and measure the solar wind, measure the mass density. Inside the magnetosphere, you can measure the magnetic field. There's a magnetometer, which is essentially just a search coil. You carry it out there and you measure the magnetic field. And lo and behold, when you compare E squared over 8 pi, whatever formula you want to, your favorite formula, calculate see what the pressure balance is, and you find that that's about right. And the pressure balance occurs at that point, the boundary, it's called the magnetopause, the boundary between the solar wind and the magnetic field. And so when the field gets, when the ram pressure gets stronger, that boundary moves in, and as you know, the Earth's field is stronger closer to the Earth. Okay, so it moves in to the point where the local field is stronger, can balance that stronger ram pressure. Okay,
So it's just a matter of B fields coming together. And
it's the B field of the magnetic field of the Earth and the ram pressure of the sun, of the solar wind.
And
Okay?
it's just this opposite. Just the B fields are resisting each other, and that's all there is to it. kind of thing.
Well, the magnetic field of the sun, the solar wind magnetic field, is not important in this. It's very weak. Okay, so that's not important in this pressure balance. What's important in the pressure balance is the ram pressure. Okay, just the solar wind speed blowing against it. Okay, and the strong magnetic field of the Earth inside, because it's just those two components to first order. You're right. If you're going to do it properly, you have to take into account.
I just-
Okay. What I want to talk about is to talk a bit more about the sun's magnetic field, and to move out from Earth orbit and talk a little bit about what happens to the solar wind and the sun's magnetic field as you move out in the solar system. Okay, I want to talk about that. I also want to come back and talk about ways of harnessing the sun's energy. And there are a couple of ways in which we can do that when we're in space. And the third thing I want to talk about is the issue of hazards. What are the hazards of being in space, and what are the ways that we can deal with these hazards? Okay. So let's go back to a diagram that I showed towards the end of Monday. Let me get that in focus, great. And remember, we have the sun in the middle, and the solar wind is streaming outwards, oops, at about 300 to 400 kilometers a second. And we have a magnetic field of the sun, which is emanating out. Now, remember we're looking down in this diagram on the sun, and we have the Earth out here, orbit of the Earth, 1 astronomical unit, and the Earth is orbiting around at about 30 kilometers per second. Okay? So that means that the Earth's magnetosphere can think of it a bit like a windsock, okay? And if we're moving this way and the wind is going outwards, then there's going to be, the solar wind isn't going to pull back the tail of the magnetosphere. It's not going to be strictly radially outwards. It's going to be aberrated, if you like, a little bit because of the Earth's motion. But because the solar wind flow is 300 kilometers a second, and our motion is only 30 kilometers a second, it's only tilted a little way. Okay? In the same way, if you were carrying a windsock in a wind, if you just held it, it would just show the wind direction. But if you were running along fast, perpendicular to the wind, then it would be deflected around a bit. Yes?
Is the solar wind relatively planar?
We're going to get to that. That's just what I'm leading up to. You're looking down, okay? And I thought it wasn't very clearly explained on Monday what the geometry of the field is. This is looking down, and as you say, what's happening out of the plane? What does that field structure really look like? I'll try an experiment here. I really don't know whether this is going to work, but let's try this. This is an eclipse picture, and I know this is very shiny, so I'm going to try and keep it still. Actually, I've got 3 pieces up. Maybe that's better. Hard to keep it flat so it doesn't shine. And you can see, this is an eclipse picture, and you can see the structure of the solar corona that's affected by the sun's magnetic field. And we can draw in field lines that sort of look a bit like this, okay? Like this, you have these things closed in here, and you can see the field is sort of streaming out. Don't worry, I'm not drawing on the photograph. It's a thing on top. Okay, so you can sort of get the idea. You might have a loop like this, so the field coming out like this, going in like this, okay? And it's not just a simple dipole, which would be just like 2 ears on either side. It's a more complicated field. This is looking sort of sideways on, looking at the sun. The field comes out more radially towards the poles like this. You can sort of see these streamers coming out like that. Of course, these streamers, head out towards the Earth. And they'll come out and we'll see them at 1 astronomical unit. If we draw this really poor sketch that I did, imitation of this, you think of the field of the sun coming out like this, and we're here at 1 AU, okay, this is the Earth. Then, as the sun rotates, okay, once every 28 days, then this structure is going to go past us, okay? And as it goes past us, it's going to look like the sheet is wobbling up and down, okay? So you can think when we're over here, we're on top of this sheet. When we're over here, we're underneath the sheet, okay? This sheet, if you like, wobbles past us. Okay, can you see that geometry? Is that a little clearer? I showed you a picture of this sheet. Think of just the sheet where the field lines turn opposite, then you can think of it as this wobbly sheet. Okay, so it is in fact a 3-dimensional structure. It's not a 1D planar field. It's actually a fairly complicated structure. It goes past us. Okay. Now, what happens when we move out beyond 1 AU, beyond the Earth's orbit to the orbits of the other planets? Well, remember that the field of the sun is attached to the sun, and so the solar wind pulls it out, but the sun continues to rotate once every 28 days, and so the field that is connected still back here to the sun makes this spiral. Okay, if you follow the field line, it becomes a spiral. Now, by the time you get to the Earth orbit, you can see that that angle is about 45 degrees, okay? The angle between the Earth's orbit and the magnetic field. But as you move further out in the solar system, that angle gets tighter and tighter, the spiral gets more and more wound. If you just look at this one here, this is going out to 25 AU, that's between the orbits of Uranus and Neptune. You can see that the spiral gets tighter and tighter and tighter, and these field lines get wrapped around on top of each other. Okay? This one here. Okay. Now, the rest of the diagram shows the same one, but we've had a blurb here, if you like. The sun has belched, as it does frequently, particularly at solar maximum, ejected some material, a fast ejection of hot gas, ionized gas from the sun. And this series of 4, if we can now zoom out, you'll see what happens. This blurb continues going in this direction, outwards, okay? And you can see it disturbs this uniform spiral and actually gets more exaggerated in size as you go further out, okay? That's one important consideration to think about. The other thing I just want to show you, remind you, is that if we have the solar wind moving out at 300 kilometers a second, remember we calculated it would be about 6 days for the solar wind to get from the sun to the Earth. But that's for just the solar wind, the regular solar wind. What happens if you produce some really energetic particles, as in if you had a big disruption event on the sun? Those fast particles would just zoom along the field, okay? They would just go zoom as fast as they could out along the field, and they might get to you within a day or so, okay? So, but remember, those charged particles follow the field, they don't go straight out. So when you're looking at the sun, and you're worried about your astronauts that are sitting out there, out in space, say on the moon in a moon base, or you know, on their way to Mars or something, you've got to think about where they are, and if you see an event on the sun, whether or not those energetic particles are going to hit them. Okay? Because if they're sitting out here on their way to Mars, and you see an eruption on this part of the sun, you know that those charged particles, those energetic particles, are going to come zooming out and hit them. So you've got to think about that when you're monitoring the sun, trying to look at its activity and predict whether or not the charged particles are going to come out and cause some damage to your instrumentation or the humans that are out in space. Come a bit more to the hazards of space a little bit later. Let me just show a slide, the first slide please, that shows this three-dimensional structure of the solar wind. This is called the ballerina skirt, and you can see the orbits of the planets. Let me see, how many have we got there? Looks like Mercury, Venus, Earth, Mars is buried, and then Jupiter out here. I think it goes out to Jupiter. And you can see this spiral, this three-dimensional spiral of the current sheet as it goes out. Okay, that's it for the slide, thank you. What happens when the solar wind goes past Jupiter, Saturn, Uranus, Neptune, Pluto? What happens then? Does it just keep going on and on and on forever? What's it going to hit sooner or later? Okay, Alpha Centauri, but before it gets to Alpha Centauri. The interstellar medium, okay? It's got a finite band, and just as the region around the Earth dominated by the Earth's magnetic field is called the magnetosphere, the region around of our solar system that's dominated by the sun is called the heliosphere. And here we have a diagram of the heliosphere, and you have to look carefully at the scale, okay? Neptune's orbit is this little circle in here. Neptune, you know, is out at what distance? What's the distance of Neptune? Orbit of Neptune? More like 40 AU. Did I get that right, or was it 30 AU? I'm getting... It's 40, isn't it? 40. Yeah, I thought so. Okay, 40 AU. How did I forget something like that? Okay. Here we have orbit of Neptune. This is a long way out. And then at some point, this supersonic solar wind that's coming out from the sun hits a barrier, because we know that outside, actually, the interstellar medium, that's just a general word for what's out there, is a very low density, and it's just a low gas. And we're moving through it, probably not at supersonic speeds. And so we have this outflowing material that's supersonic, and it's got to somehow have a transition into the subsonic region outside. So there has to be a shock. This is the shock front here, this dashed line. And then outside there's this thing called the heliopause. It's this thing here, which is this boundary between the two, separating the two gases. Now, big question is, where is the heliopause? And we don't know. Currently, a good rule of thumb is it's 10 years further than the furthest spacecraft that we've got. Because we used to think it was out at about 30 AU. And then Voyager got out there and we discovered, no, it's not that far. So everybody sort of projects that, well, soon Voyager or Pioneer will go through this shock front. But this projection has continued to go further and further as the spacecraft go out further and further. And we really don't know how far it is. But it's been 10 years beyond the furthest spacecraft for the past 20 years, okay? So who knows really how far it is. It could be anywhere between 100 and 200 AU, okay? And I've drawn on this diagram. Is it in your notes, these extra arrows? The directions of Voyager? Well, the spacecraft, I can show you this later, but Pioneer is going down the tail. Pioneer 10, Pioneer 11, Voyager 1 and Voyager 2 are all going upstream. And the chances are pretty good that, well, we're hoping that Voyager 1 will go through. Voyager 1 is the one that's actually the most likely to go through the front, hit this shock front, and then later the heliopause. And so they're keeping Voyager and the Pioneers still tracked occasionally, just in case that we go through this boundary. Try and find out where it is.
What's forcing the oval shape?
Well, in the same way that the Earth's magnetosphere is an oval shape because of the solar wind hitting the front, pulling the tail back behind, our motion, the solar system's motion through the local medium, okay, is causing this flow around it. Okay, it's all a matter of relative motion, one thing relative to the other. Okay, so it's the solar system moving through the local medium that causes that shape. Finally, I just want to mention a exciting upcoming event this Saturday, February the 8th. The NASA ESA, European Space Agency mission Ulysses, is going to reach Jupiter. And let me tell you a little bit about Ulysses. The main point of Ulysses is to escape from the ecliptic plane. All of the spacecraft, as all the planets are, confined pretty much to the ecliptic plane. And the whole point of Ulysses is to go from Earth out to Jupiter and use the mass of Jupiter to do gravity swing by, and it's going to go over the north part of Jupiter and then down south and head down south of the ecliptic plane, out past the sun, just a little outside 1 AU, and then go over the North Pole, over like this, okay? And measure the solar wind and the interplanetary medium at the pole regions around the sun, which nobody has any idea what's going on out there, okay? And so 8th of February, this Saturday, watch out, it may be on the news. There aren't going to be any pictures, there's no cameras on this. It's purely particles and fields. But you may see on the news a video of the Io Taurus material that's trapped in the Jupiter's magnetosphere that was made by somebody on the faculty here at CU, Nick Schneider, takes these pictures from the ground. He's in fact down there in Arizona looking at Jupiter right now, looking for the particles that are trapped in Jupiter's magnetosphere and watching them from the ground as Ulysses flies right through the plasma. So maybe this will hit the news, but there aren't any pictures, so maybe if it's a slow news night, we may get on the news.
Why no pictures?
Why no pictures?
Wait.
It's a particles and fields experiment. The whole point is to go and measure the particles in the fields, and we can take pictures of the sun from the ground. We don't need to go into space to do that. It makes it a lot cheaper. It's a spinning spacecraft. The technology is a lot easier. The telemetry rate is a lot lower. Pictures cause a lot of problems if you want to take pictures. It makes emissions many times more expensive, but more glamorous, I guess, too. Okay. I want to change tracks now and talk about the other type of radiation. That is, instead of the charged particles, electrons and protons, we're going to talk about photons. Okay? Electromagnetic radiation.
Can we go back to the solar wind for just a second?
Yes. What's your question?
The solar wind follows the magnetic lines.
No. Let's get this straight, because this is easy to get really confused with. Okay? Let's go through this again. The solar wind flows out radially outwards from the sun, and it carries with it, okay, the magnetic field with it. Okay, so if you think of, I'm running out of colors here. Let me I'll stick with blue. If you think of a particle of the solar wind that's here, okay, it moves radially outwards. Okay. And at some point, it reaches out here at the Earth, okay? And it carries with it the magnetic field that was with it, okay? But that magnetic field line that it's carrying with it remains attached at one end to the sun back here, okay? So by the time it gets out to here, it's pulled with it a string, if you like, of the magnetic field, and that string is still attached to the sun. Now, in those 6 days that the Earth, that blob of solar wind has taken to move out to one Earth orbit, the sun has revolved about a fifth or more of its way around. Okay, and so if you like, that piece, it's pulled that piece of string around, so the field is then pulled around in a spiral. Does that make sense?
Yeah, that's what I thought I remembered from Monday, but I think a little earlier you said that that there were particles that were following along the lines, and
Okay.
that's what I'm confused about.
Right. Okay. The solar wind, you can think of the wind as a sort of passive wind. It's most of the stuff that's coming out from the sun. Okay. Now, what happens if there's a really energetic event on the sun? Okay, a big flare and materials thrown out, the sun's just gone nuts. Okay, it's just a blurb of stuff. And amongst that, there's going to be stuff that's much more energetic than the average solar wind. Okay, really energetic particles, MeV protons and stuff like that. Okay, they're not going to hang around for the solar wind. They just get out. Okay, and say we took this same field line. Okay. The solar wind that's taken 6 days to get out there, the energetic particles that came from the same blob where that field line is attached would then come streaming out, paying no attention to the solar wind, but following the magnetic field really fast. Okay, so it's the energetic ones that follow the field lines. Okay, does that make it clear?
Yeah, that's good.
Okay, great. Okay, so now let's talk about that other form of radiation, the solar radiation. And here we have a spectrum where we have wavelength along here. And you know that most of the sun, the radiation from the sun is in the visible range, vis. And then to shorter wavelengths we have UV, ultraviolet. Longer wavelengths we have what kind of radiation at longer wavelengths? Infrared, IR. Are these terms familiar to you? Okay. And out towards the radio. furthest, okay. And you know that most of the sun the radiation that comes from the Earth, the sun is in the visible range, okay. Our eyes are tuned to the sun so that they're adapted to deal with the fact that most of the sun that's coming towards us and sunlight is in the visible range. Now, we have here several things plotted. The dotted curve is what you would expect from an object that's at 5900 Kelvin, an object that has a temperature of 5900 Kelvin. And that's pretty much the surface of the sun. The photosphere has a temperature of about 59 Kelvin, and so it would produce this characteristic, it's called a black body, even though that we all know the sun isn't black. It's just the name of the characteristic shape of something that has that sort of temperature. Now, there are two other lines here. There's the top part of the green shading here is the spectrum at the top of the atmosphere. That is, if you put a spectrograph above the Earth's atmosphere and measured what is the distribution of light as a function of frequency, this is what you would see, the top of that envelope. Now, of course, as we've discussed, the atmosphere absorbs a lot of sunlight, but it doesn't just absorb it uniformly, it absorbs it preferentially at different wavelengths. And in particular, here is our friend ozone. Remember, Susan Solomon discussed how the upper atmosphere absorbs ozone, absorbs ultraviolet sunlight, very important to keep us from burning up. And then at these different, you see these dips, these strong dips, correspond to absorption due to water, carbon dioxide, some ozone and other frequencies, but mainly water vapor in the upper atmosphere absorbs a lot of this sunlight. So that when we look at sea level, we have the lower part of the spectrum. Okay. Now, if we are above the Earth's atmosphere, we can think about this sunlight that's coming in and hitting up the upper atmosphere. And this sunlight is impinging on our spacecraft, and it's a fair amount of energy. Let's put it to some good use. Okay? And you know very well that spacecraft users, they have solar cells on them. If we could have some slides, I wanted to show you some pictures of some solar cells on spacecraft. Start off with the Hubble Space Telescope being launched from the shuttle bay. And you can see here the solar panels being rolled out. They're sort of like Venetian blinds being rolled out, excuse me, mechanically on the sides of the Space Telescope, and it's these solar panels that provide the power to the Space Telescope. The next picture shows a futuristic picture of what things will be like if you excuse me, had a space station which is going to rely on solar power. You're going to have huge panels. And here we have our astronauts repairing the the panels, of the space station. Okay. Can we have the next picture? I'm not certain that this is. No, it was the blank. Okay. What I want to just show you. Yeah. Okay. That's it for the slides. Thank you. I want to show you a picture. This is from your book, your textbook, Intro to Space, and on page 72, this doesn't show very well on the camera, but you can look in your own copy of the textbook. There was an experiment where they took an array of solar cells and put them on a zigzag, like a zigzag blind, and extended it out from the shuttle bay, and it had dimensions of about 14 feet across this way, by when it was fully extended to 105 feet, okay, way out, huge solar panel. And this was made of very thin material, and this was just a test of the mechanics. But ultimately, such a solar panel could produce something like 1.25 kilowatts. Okay, and that's a lot of energy. That's enough to power a fairly large spacecraft.
And it
Yes?
said it folded only into 4 inches.
4 inches in, yeah, right. I mean, it would be about 14 feet by 4 inches high. Yeah. Okay? So these are very, very thin films. Okay? Let's talk a little bit about solar power. Things are changing really fast. The photovoltaics are really improving, and there's a big change is occurring. Currently, the efficiency is on the order of 14%, okay? But with new technology, using new semiconductors, not the old ones use silicon, now they're using things called gallium arsenide, things like that. Anyway, they're improving towards the sort of 28% efficiency, okay? Considerable improvement. Now, the sunlight at 1 AU is about 1,400 watts per square meter, okay? Now, this is above the Earth's atmosphere. Down on the ground, even in the hottest sort of equatorial skyless regions, it comes down to about 1,000 watts per square meter. But if you're out in space, without the atmosphere, you've got the full 1,400 watts per square meter. Okay, so that you can think of that in terms of 1,400 watt light bulbs, okay? That kind of energy being dumped onto an area of a square meter, okay? And these solar cells, you know, they used to be the sort of size of a postage stamp. That was the sort of size of the unit cell. And now they're getting to be, you know, fairly large size. And they're making them larger and larger and more efficient. Per cell, right, okay. And each cell, you would have something like half a volt across it. What's happening is the sunlight is hitting a semiconductor. Those photons are coming in and hitting the semiconductor. And because of the property of the semiconductor, which I'm not going to go into, you end up generating a voltage across it. And then if you add all those voltages in series, you can get a large voltage. Okay, half a volt doesn't do you much good, but you add them together and you can get a decent voltage. Alternatively, you can put them in parallel and add up the current that you can get out, okay, and get a decent current. Depends what you want, whether you want current or whether you want voltage. But the product of those two, as you know, watts times amps equals volts, is the total power that you get out. The wattage is power is on the order of, right now, about 200 watts per square meter. Okay? So we have a, you know, this corresponds to these sort of efficiencies. If you've got 1,400 watts coming in from the sun, you're converting that solar energy into electrical power, okay, of about 200 watts per square meter. Now, say you have a big spacecraft, you might need something like 1,800 watts. Voyager actually, the RTGs produce something like 800 watts, okay, much less. But if you've got a big thing like TDRS, you know, those telecommunication satellites, they would be needing more like 1,800. Space station, you need much more. Then that means that you need 9 square meters of solar cells. Okay, 9 square meters means 3 meters by 3 meters. That's 10 foot by 10 foot. Okay, fairly large panel, but moderate. But the weight of these solar cells is such that they are, paper here, move that up. We have the weight of these is about 22 watts per kilogram. So if we want this value of 1,800 watts again, that means that we need the mass of solar cells must be on the order of 82 kilograms. Okay? That's a fair mass, actually. It's quite a lot to deal with. You've got to think about getting it up to space. But it's your source of power. Okay, so power always weighs a lot. That you can never get around that. That's always a problem. Okay, but this is probably a more efficient way than using RTGs, radio thermoelectric generators, which finally have some finite lifetime. Okay, now let's get into this is the sort of current usage, and these solar cells are either put on wings on the outside, and you're used to seeing how these wings are sort of tilted to keep facing the sun. As the satellite goes in its orbit, they keep moving the solar cells, so they keep facing the sun. Or you can wrap the solar cells around the spacecraft, around the bus, and so one side is always facing the sun. But there's a novel use of solar power, which is solar sailing. And that is to take the power of the sun, and this is I have to really emphasize here that this is not, I'm getting confused, here we are. This is not using the solar wind. I mean, you think of wind, sailing, no, forget it, no. This is not the solar wind, this is the solar photons, okay, solar radiation, hitting a solar cell, okay, and sailing using electromagnetic radiation. And if we zero in on here for a minute, let me sort of explain this. We have photons coming in and hitting, light from the sun, hitting a surface. Okay? Now, if you have something coming in and hitting a surface and recoiling, then the momentum of the object that comes in and hits the thing, and if it recoils, then it actually delivers twice as much to this thing that it hits, obstacle that it hits. Okay, you've got conservation of momentum, 1 unit of momentum coming in, hitting, and then 1 unit of momentum going away in the opposite direction. Momentum is a vector quantity, so that if you have plus and then you've got minus, you've got twice as much to conserve momentum, twice as much has to be delivered to this object. Okay, so that if you have a panel like this being hit by sunlight, then it receives a force due to this impulse of the photon that forces it in this direction, okay, perpendicular to its surface. So that means that if you have some large object, spacecraft, that is in orbit around the sun, okay, not in orbit around the Earth, receiving it, so it's going around like this, which is obviously perpendicular to the direction of the sunlight, then if it receives a force like that, okay, then it will be giving it some momentum so that its trajectory moves outwards, okay? It's moving away from the sun. Or if you want to slow down the spacecraft and so it loses angular momentum and comes in towards the sun, you just tilt your solar cells in a panel in the other direction, and so it loses momentum, angular momentum, and goes in towards the sun. Okay, so you can use this effect of the sunlight hitting a big panel to direct your spacecraft around the solar system. Now you may think, wow, sunlight, what kind of power does the sunlight provide? What kind of impulse does these photons produce? Well, it's not very much, and I'll go through some numbers in a minute. But if you have something like this is a sort of scheme where you have a tiny little payload, a camera. Do you want to go and look at some asteroid with a huge set of solar panels, and you're not in a desperate hurry to get to wherever you're going? You could imagine cruising around the solar system using this tacking in, tacking out, using the solar electromagnetic radiation to take you from one asteroid to the next to take pictures. Okay, relatively cheap, very slow. It's not slow. I mean months to years, not shorter. Then you can get around using solar energy. Actually, okay, let's look a little bit at look at a little bit of this quantitatively. Okay, I'm going to go through this calculation for solar sailing. to give you some idea of the sort of quantities that we're talking about. Okay, a photon has momentum. Now, it doesn't actually have mass, but it does have momentum. And its momentum is equal to its energy divided by c, speed of light. The radiation pressure is equal to the power per unit area divided by c. The power delivered per unit area divided by c. Now, we know that the sun, the light pressure provided, supplied by the sun, it's a better word. We know that that sunlight is reflected, and remember we have this factor of 2 due to the fact that the photon delivers twice as much the momentum to the object. So we have a factor of 2 times the power per unit area of sunlight at 1 astronomical unit, which we said was 1400 watts per square meter, divided by c, the speed of light. Now, remember that if you go out in the solar system, then this is going to decrease, and it decreases as 1 over r squared. The power delivered by sunlight decreases as you move out by 1 over r squared. But the force, okay, let's write down the force is equal to the pressure times the area, okay? So if we have a solar cell, and let's just make a rough estimate, solar cell of radius r, the area is what? Area of a circle, radius r? Pi r squared. So now we have that the force is equal to, F is equal to 2 times 1400 times pi r, radius of our solar panel squared, divided by c again. Now, if the mass, that's the sail plus the payload, okay, because you've got to accelerate the sail as well as your solar panel, as well as the payload that you want to carry there, your camera or whatever, is, let's call it mass m. Then we have an acceleration. Remember that F equals mass times acceleration, okay, Newton's law. Now acceleration is then just equal to the force divided by the mass, okay, that you're trying to accelerate. And so you have an acceleration now of 2 times 1400 times pi times r squared divided by the mass and c. Okay, so this is the mass of the payload. Okay, so what does this mean? Well, if you plug in the numbers, and I recommend that you go through this calculation and go through the numbers yourself, you will find you get something that is like 3 times 10 to the minus 5 times r squared over m meters per second. Acceleration is velocity, rate of change of velocity, so meters per second, velocity, change per second. And that means then that if you want to take the mass equal to 1 kilogram, and that is being super optimistic, okay? Mass of a payload and the mass of a huge solar cell being 1 kilogram. But let's just be optimistic. You guys believe in science fiction. That's okay. And we want to accelerate it to, say, 1/10 of g, right? 1/10 of the Earth's gravitational acceleration that we feel here on the Earth. Okay, we want to accelerate it to 1/10 of a g. That's not a lot of acceleration. Then that means, if you plug this in, you'll find that means that R, the size of our solar cell, okay, has to be about 185 meters. Okay? So that's, 400 meters across, more or less, a little less. Okay? It's pretty big. Is that about half a football field? I'm not very good at American football fields. Something like that, okay? It's pretty big. So you could have a small mass, a very feather lightweight sail, and you have a slow acceleration of about 0.1 g. And so you could take a camera, and it's a very slow acceleration, but you know that if you accelerate for a very long time, eventually you will get up to a large speed. So say you wanted to take a camera to Alpha Centaurus, or outside the solar system, you could put it on a solar sail and send it out. Take a long time, but eventually it would get there with very, very little energy requirements. Okay? So this is an idea that's fairly new. It's actually been around for a while, but only recently beginning to get recently used or thought about as a means of traveling. But there are various ideas of how you could use a solar sail to move around in the solar system or outside the solar system, interstellar travel. Okay, now I want to move on to the final topic, and let me just write this up on the board because I want to leave this up here while I show you some examples. We're going to talk about hazards of being out in space, okay? And one of them is that of radiation. And what we're talking about here is really not electromagnetic radiation, because the electromagnetic radiation from the sun is not very severe, except you've got to worry about X-rays. If you're down on the ground, X-rays from the sun don't get through the atmosphere very far. But if you're up in space, then X-rays from the sun will hit your electronics and hit you as a human being sitting in space. So you have to worry about X-rays from flares, from solar flares. Now, you may be saying, well, what the heck is a flare? Gary Heckman is going to tell you about this, a lot more about this when he talks about the sun. But let me just write that up as something to think about. And what you have to think about is forecasting. Okay, when are these things going to occur? What is the forms of protection? Or maybe you just have to build in redundancy. I hope that's spelled right. I think it is. Okay, so that's one form of hazards. The other thing that we haven't talked about much yet is the issue of debris, junk, physical matter out in space. And there's two issues. One is the natural hazards, and the other is artificial. And when I say artificial, of course I mean man-made, human-made. Okay, so those are the... Can you read that in the Springs?
Yes.
Mark and Tom? Okay, I'm going to go through these fairly quickly. Okay. The hazard of radiation. This is a serious hazard, and it really isn't clear. This is really just being studied seriously. It is extraordinary that the astronauts that went to, the Apollo astronauts that went to the moon, and they were going around the time of a lot of solar activity, they were extraordinarily lucky not to get hit by a major proton outburst from the sun. They were just darn lucky. Because there are times when you're up in space and the sun dumps these energetic particles into space, and there's very little you can do about it. You could, to keep X-rays out, it's a little easier. You can put some fairly thin foil will keep X-rays out, but very little will keep energetic particles out. You will need to have thick quantities of lead. You don't want to carry lead into space. One thing you think about if you're going to Mars is you're going to be in orbit, you're going to be on your way to Mars for 6 months or more. Novel idea, not very nice to think about, is you're going to produce 6 months worth of sewage. Turns out sewage is very good for protecting you from radiation. Bizarre though it may sound, surrounding yourself, encased, of course, with a layer of sewage around your spacecraft, filling the tanks with sewage actually might protect you from a solar flare. Interesting thought, not a very cheery one, but worth thinking about. You nodding your head in disbelief? Interesting, right, interesting. Okay, but there is some forecasting, and Gary Heckman again, who was involved in the Solar Environment Lab here in Boulder, is involved in forecasting the activity on the Sun and trying to predict when various things are going to hit the Earth or various spacecraft in space. He'll talk more about that. Protection is a little difficult to do, or you can just build in redundancy, have twice as much electronics, or allow for the fact that your electronics is going to get zapped with radiation, and you have to allow for the fact that it's not going to work perfectly. You have to allow for some inefficiencies. Okay. Now, when we talk about debris, there are a couple of things. Obviously, natural debris, there's nothing you can do about it. This is a piece of debris from space. It's in fact a tektite, as you guessed, which means that it's probably a lump of lava that came from the moon. This is a moon rock. And this came in through the atmosphere, and as it came in through the atmosphere, it actually was pulled out. This is, I think, another half that would come out like this. It spun and produced this sort of funny shape, and it's all sort of dimpled and lumpy. And this was presumably a lot larger when it hit the top of the atmosphere, and a lot of it was removed as it came in, evaporated. But this hit the ground. Okay. Now you know that the Earth has been bombarded with stuff since the beginning of time, and some of it reaches the ground, and some of it doesn't reach the ground. Stuff that doesn't reach the ground, of course, the meteoroids, they will be out in space then. Okay, so your spacecraft that's above the Earth's atmosphere is going to be bombarded with these things. Some of them are fairly large like this. Some of them are, huge chunks. Very few of them. Most of them are tiny little specks of dust. But a small speck of dust moving at the low Earth orbit speeds, that's a few kilometers per second, can have the same sort of force as a bowling ball hitting you at 60 miles an hour. Okay, so you have to encase your stuff on your spacecraft with some kind of protective blanket. Okay, and there's been a lot of study of space debris, both natural and artificial, recently, because of the getting spacecraft back that have been sitting out in space for a while, like the LDEF, various other spacecraft that were recovered. Looking at them, we learn what is the impact out in space. So you have to allow for this. If it's natural phenomena, there's not much you can do except for keep your fingers crossed, because you're not going to change that. The artificial debris is another issue, and this is increasingly a concern for low Earth orbit, becoming a very serious issue in low Earth orbit. And the chances now in low Earth orbit are being hit by man-made objects in fact exceeds that of being hit by meteorite material. There are there have been 19,000 launches since the dawn of the space era 30 years ago. And there are, in fact, 7,000 orbits being tracked in space. And the US Space Command, down the range a little way, here in Colorado, are involved with the monitoring of these large quantity of material that's in space orbiting the Earth. They use 20 radars and 8 optical tracking facilities around the Earth, looking up in space and trying to keep track of these 7,000 objects that are in space at the surveillance center. And they can detect all sorts of objects. In your notes, you can see this diagram here that shows this is the diameter, the limiting diameter, for 2 techniques. One is radar. Objects that are fairly close can be detected with radar. This is altitude up here on the left, up this vertical axis. Things that are further than about 5,000 kilometers can be tracked by their reflecting sunlight, the sunlight that they reflect. And those are the things that you see when you look at see something orbiting every 90 minutes, you see something go by in the sky. They can be tracked. Objects that are as small as 10 centimeters, that's, this size, okay, can be tracked by radar lower down and optically much higher up, okay. But those are just objects that are this size and bigger, the size of an astronaut's glove. You remember that one of the astronauts lost a glove and it's been in orbit ever since. At least I think it's still in orbit. Maybe it's come down. But what about the small objects? There are a lot of small objects that are not detected, and these stay in space. Okay. Eventually, they will decay and hit the ground, but most of them keep going. This is a plot of altitude this way in the cross-section area, the prediction of the number of impacts per year. If you're out in space at, say, an altitude of 500 kilometers, then you can expect to receive 10 to the minus 6 impacts per square meter per year. Okay, well, that doesn't sound very much. That means that if you have a spacecraft that's 1 meter in cross-section, then you have to wait 1 million years before you get hit. Okay, big deal. Well, what happens if your spacecraft is worth several $1,000,000 and you happen to be that poor, unfortunate spacecraft that got hit at the beginning of those 1,000,000 years, not the end of that 1,000,000 years? Okay? There's a probability involved in here. And the insurance business is fully aware of this concern. Okay. Now, what eventually happens? Well, they eventually re-enter, burn up, and if you're down at lower Earth orbit, you will burn up more quickly. And if you are at a time of solar maximum, where the Earth's atmosphere is extended, heated up, and then things will re-enter more rapidly. I'll just show you very quickly a plot of, this is year, this is flux impacts per square per year. If you're out at 800 kilometers, then the orbital debris, it's increasing with time because there's more stuff up there, but it doesn't change, it's just continuous. The low at 400 kilometers, you'll see there's this wiggly line, and these points of minima occur at solar maximum, when there's a maximum amount of re-entry and material being removed from the upper atmosphere. Okay, well, what do we do about it? If you are below a certain altitude, it's easier to have forced deorbit and get the stuff to re-enter. If you're above a certain altitude, about 300 kilometers, it's less energy to send something up and push it away from the Earth. Okay, so the next decade is going to be a major concern, cleaning up the Earth space environment to make it safer for objects, spacecraft and humans to go out into space. Okay, well, that's it. I've given you a feel of the space environment and there's various things out there. Thank you.